I was very much looking forward to coming to the Netherlands last year, and it's a great shame that I was not able to come and meet everyone and participate in the conference. Actually meet people face to face, but it is what it is, as a famous politician once said. Okay, so the title of my talk is Number Theory and Fast Arithmetic, and what I'm going to be talking about is I will start with a bit about fast integer arithmetic, so the history of the problem, mainly multiplication, and what is the state of the art for this problem. But most of the talk I'll be discussing applications of fast arithmetic in number theory, and these are applications that have come up in my own research. So I'll give mainly three topics: Wilson primes, Bernoulli numbers, and irregular primes, and how fast arithmetic has been used in these different areas. And I discovered while writing this talk that you actually learn a lot about the history of computation, early hardware and software issues in computation. And so I've tried to weave that into the story a little bit, and there's lots of interesting bits and pieces that come along. So let me start with fast integer arithmetic. So the starting point is multiplication. So I'm looking at the problem of multiplying integers with n bits. If you like, you could do n digits in base 10. It doesn't really matter. I'm going to stick to binary. And I'm going to write m of n for the cost of multiplying n-bit integers. The exact computational model doesn't really matter. I want you to think of just logical operations on single bits. That's what I mean by bit operations. If you like, you could think of the Boolean complexities, the number of logic gates in a Boolean circuit, for example. It doesn't really matter too much. So the first multiplication algorithm we learn is the classical algorithm, or long multiplication. So here's a brief illustration of that. And that is a quadratic time algorithm because you have to multiply every digit of the first number by every digit of the second number, and then you have to add up all these products that you've computed in the right order. So that is an n-squared algorithm. Around 1956, the famous Soviet mathematician Andrei Kolmogorov proposed that is in fact the best you can do. He conjectured that that the cost is actually big theta n squared. So that is an upper and lower bound up to a constant. And his reason for thinking this was explained much later by Karatsuba. Karatsuba said, probably the appearance of this conjecture is based on the fact that throughout the history of mankind, people have been using this quadratic time algorithm, and if a more economical method existed, it would have already been found. So this is basically an argument from ignorance. We've been trying to do better and we can't, so that must be the best we can do. Now, of course, it's not the best we can do, and Karatsuba, when he was a student, attended a seminar series that Kolmogorov had arranged on this topic, and very quickly he discovered what is now known as Karatsuba's algorithm, which was the first subquadratic multiplication algorithm. So the complexity, so you can see my mouse cursor here. Yep. So the complexity here is less than n squared, n to the roughly 1.58. And there were many improvements during the 1960s. I haven't listed them all, but the sort of pinnacle of this line of research was Donald Knuth. He gave this algorithm with this somewhat ugly-looking complexity bound. In fact, he didn't actually give a proof. It's given as a series of exercises in the Art of Computer Programming, Volume 2. I don't know how many people have done those exercises, but I worked through them, and they're actually quite difficult. But you get this running time bound, which is almost linear in n. Then we have the result of Schoenhager and Strassen in 1971, and this really changed the game. They brought the fast Fourier transform, which had only recently become well known, and they were able to prove this n log n log log n bound for integer multiplication. And they also conjectured that in fact the log log n is superfluous, and you should be able to get n log n, and that in fact this is the best you should be able to do. I don't know exactly why they thought that was the right answer, but this is what they wrote in their paper. So nothing happened for a very long time, and then in 2007, so more than 3 decades later, Martin Führer, who's a Swiss computer scientist based in the United States, he managed to improve the log log n factor to this k to the log star n. So log star is the iterated logarithm. It's the number of times you have to hit a number with the log function to bash it down to 1. So it's a very, very slowly growing function. And this result was a tremendous surprise. You know, I don't think anyone was really expecting that to happen. I remember when it came out, I was a graduate student and I just went for a very long walk around my neighborhood. I walked and walked and walked until I convinced myself that they understood what they had done, because what he had done, because it really seemed quite fantastical at the time. And then more recently, Joris van der Hoeven, who's probably well known to this audience, he is a Dutch mathematician working in France. And so he and I wrote a paper where we improved this to n log n, so matching the upper bound that Schoenhagen and Strassen had conjectured. And this was officially published only a few weeks ago. So I don't have time in this talk to go into how any of these algorithms work, unfortunately. So once you know how to multiply quickly, then you can do a lot of other things. So just very briefly, and all these reductions were known by the 1970s. You can divide. So if you want to divide two large integers, you can reduce that to multiplication using methods such as Newton iteration. So you can compute quotients and remainders in essentially the same running time, so up to a constant factor, m of n. So now we know that's n log n as well. You can compute integer parts of the square root of an integer. You can compute GCDs quickly too. You give up a log n factor when computing GCDs of n-bit integers. You can also do floating point arithmetic. So if you're doing arithmetic on real numbers with n bits of precision, you can compute products and quotients and square roots and so on, all in the same running time of m of n. And then when you go to more interesting functions like trigonometric functions, exponential functions, and so on, again, you pay a log n. And then similar results are known for polynomials over finite fields and other interesting coefficient rings. So really multiplication is the building block. Everything else builds on that, I guess, with a notable exception of matrix multiplication, which is a problem that I know very little about, but sounds like a very interesting problem to think about. Okay, so that's all I want to say about fast multiplication. I'm going to spend the rest of the talk discussing a few applications that have come up in my research. So the first one I want to talk about is Wilson primes. So first of all, I'll remind you about Wilson's theorem. So Wilson's theorem is something in elementary number theory that we would do in any elementary first number theory course. It says the following: if you have a prime number p, and you look at p minus 1 factorial, then that is equal to minus 1 modulo p. So this is quite easy to prove once you know what you're doing. It was first stated around 1000 AD by an Arabic mathematician known as Alhazen. And he did a few things in mathematics, but his most famous work is actually in optics. He was the guy who first suggested a theory of the theory of human vision, which works by light reflecting off objects and bouncing into your eye, as opposed to the other theory that was popular in ancient times, is that there's some kind of some like laser beam that comes out of your eye to the thing that is being seen and somehow picks up the information and returns it to your eye. So he argued for the modern theory. As far as I know, this Wilson's theorem was first proved by Lagrange in 1771. I don't actually know exactly why Wilson's name is attached to this theorem. I presume that's in Wikipedia, but I don't remember the answer to that question. Okay, so that's Wilson's theorem. So Wilson prime is a very special prime that satisfies the same congruence, but instead of modulo p, it's a stronger congruence. It's modulo p squared, so an extra power of p. So another way to say that is if you form the Wilson quotient, so that is, you take p minus 1 factorial and you add 1, and then you divide by p, so that's an integer, that's by Wilson's theorem. And then you look at that quantity modulo p. And if that quantity is 0, then p is a Wilson prime. Okay. So the first Wilson prime is 5, and that's easy to see because 4 factorial, that's p minus 1 factorial, is 24, which happens to be minus 1 modulo 25. And the next one is 13. And you can just calculate that if you want. Interesting challenge to try and do that by hand. You might spend the rest of the lecture doing that by hand if you get bored of my talk. The first mention I found of p equals 13 is in a very nice book from the late 19th century by Matthews called Theory of Numbers. He mentions p equals 13. So the first computational problem I want to talk about is if I give you a bound n, maybe some very large number, how do you find all the Wilson primes less than n? So the first thing you might do is you might say, well, how do I compute one of these Wilson quotients? Okay, and the obvious thing to do is you do what I did on the previous slide. You write down the factorial and then you divide by p squared. Now the problem with this is that the factorials get very large, and you can already see 12 factorial is already starting to get a bit big. So this is a lot of work. So you can do a little bit better than this using this very simple idea, which is one of the key ideas in computational number theory, is that you should reduce modulo your modulus as often as you can. So what you do is you just start with 1 and you multiply by 2 and you multiply by 3 and you keep multiplying, and then very frequently, maybe even every multiplication, you reduce modulo p squared. You divide by p squared and take the remainder. So you never have to deal with numbers bigger than p squared. And if you do this, the time it takes you is roughly proportional to p. It's roughly linear in p because you have to multiply by p things. So there's a bunch of identities which have been proved over the years which let you save at least a constant factor of the work. So here's the simplest one. It expresses p minus 1 factorial in terms of p minus 1 over 2 factorial. This is a congruence modulo p squared. So you only need to compute a product that's half as long. There are these extra factors here, the 2 to the p minus 1 and so on, but these are actually very easy to compute. There's an algorithm called repeated squaring or binary powering, which lets you compute these efficiently. So really the deal here is to compute this half-sized factorial. So this formula appears in Matthew's book. He doesn't give a proof. I don't know if he expected the reader to find a proof. It's not that hard to prove if you just sit down and play with it for a while. The first proof I found written down was actually by Beeger in 1920. So this is nice that I actually get to mention Beeger's work in the Beeger lecture. I don't know if it's traditional to mention Beeger in the Beeger lecture, but perhaps this could be a challenge for future Beeger lecturers to try and seamlessly work Beeger into their lectures. So Beeger used this to compute the Wilson primes up to 300. So he actually did this computation by hand. And you can see that he's interested in computational complexity, right? The fact that this identity is saving him some work. Obviously, if you're doing this by hand, that's really important. But he's also interested in something that modern computational number theorists are interested in, which is correctness. If you're doing a big computation, you're going to make mistakes. How do you avoid mistakes? And he points out that you can use Wilson's theorem, this identity, to check that you haven't made any mistakes. Because once you've computed it modulo p squared, you can check if your computation is correct modulo p. So here is a table from his paper. So he's listed all the primes in these 3 columns. He's listed all the primes up to 300. And for each one, you can see he's got this second column here, which is the WP. That's the Wilson quotient I defined before. And you can see for 5 and for 13, he gets 0. So that's showing those are Wilson primes. So this is a paper in a journal called Messenger of Mathematics, which I think is a very cute name for a journal. It later became, I believe, the Quarterly Journal of Mathematics. So it doesn't exist under that name anymore. But one interesting thing about this table is actually it does contain a bunch of mistakes. So 5 of these numbers are wrong. So despite his correctness check, there are still some mistakes. And this is very easy to check now, of course, with a modern computer. I can do this in a very small fraction of a second. It's interesting, these mistakes are clustered together. So my theory is he was doing those computations at 3 in the morning. So I also make lots of mistakes at 3 in the morning. I've proved some of my finest theorems at 3 in the morning, which have turned out subsequently to be complete rubbish. So then the search for Wilson primes moved into the computer age in 1950. So a fellow named Goldberg ran a search using this machine here. This is the Standard Eastern Automatic Computer. So this is an interesting computer. It's one of the first stored program electronic computers. So it meant that it actually stored the program it was going to run in its memory. I believe the memory was about 3 kilobytes, which is pretty small by modern standards, but it meant that you had to be a very clever programmer to use this machine. So stored program is in contrast to, for example, the Harvard Mark I, which was a little bit earlier, which ran on punch cards. The program is fed in on punch cards, and the machine can only operate as fast as it can read the punch cards. And another type of computer at the time, the ENIAC, for example, was a machine that was was an electronic machine, but the way you programmed it was by attaching all the wires in the right places. So it was very time consuming to program. This one, you could actually feed in the program, I guess, presumably on punch cards, but then the program is stored in the memory and could run at electronic speed. So this was a big deal. You could run a loop in a way that you could not do on the earlier machines easily. So he went up to 10,000 on this machine, and he found the third Wilson prime, which happens to be 563. So here's a table of subsequent computations of Wilson primes that were done up to 2008. So a few interesting points. So first of all, I've mentioned this, so that this table does not seem to be monotonic. I've got this entry here. This is Emma Lamer, and the reason is that she didn't make any mistakes. So I thought it was only fair to include that entry in the table. This one is quite interesting. Why did they go up to this strange number, 18 million something or other? It was because of a power failure. Okay, the whole computing center shut down, and they didn't bother to switch on the program afterwards. So I don't remember if that's ever happened to me, but something one has to contend with in real life. And there's a couple of well-known contemporary mathematicians here. Richard Crandall died a few years ago, unfortunately. Carl Pomerantz, Carl Dilker, still around. So I got involved in this problem in 2014 or thereabouts. And we went a lot further. So this was done with my colleague Edgar Costa, who's at MIT, and Robert Gerbitz, who at the time was a master's student, in fact. And I think his contribution was definitely the most important to this work. I'll talk a bit more about that in a few moments. So what we did is we went up to 20 trillion, and we didn't find any other Wilson primes, which is actually not that surprising. I'll say more about this in a moment. But I just want to give an exercise to the audience. So for this particular prime, 16,556,218,163,369, for that prime, the Wilson quotient turns out to be 2. That's the smallest non-zero Wilson quotient we found. And I think if you think about how you would verify that, you'll see that it's quite a challenging problem, even with a fast computer. And it gives you some idea of how difficult it is to check every prime up to 20 trillion, which is what we did. Okay, so about this question about how many Wilson primes we expect. So heuristically, you might guess that this WP, this is a number modulo P, and it should be sort of uniformly distributed, whatever that means. I mean, it doesn't quite make sense because it's really deterministic, but you could try to formulate that statement in a probabilistic way, something about density, for example. But anyway, you would expect that the probability that you get 0 is 1 over P. So according to these heuristics, this log x growth, we should expect about 3.7 Wilson primes up to 20 trillion. And in fact, we've seen 3. So these heuristics are pretty reasonable. Okay, I want to talk a little bit about algorithms for computing these Wilson quotients. So the first thing I want to say is that I mentioned a linear time bound before for computing the Wilson quotient, WP. In fact, there is a faster algorithm which runs in essentially square root of P time. So the basic idea goes back to Strassen, and it depends heavily on fast arithmetic. So this is an example of fast arithmetic being used for this problem. So I'm going to explain roughly how this algorithm works. So I'm going to take the square root of P, which is I'm going to call n. I'm worried I've dropped out again. Am I still there?
Yes, everything is still fine.
Okay.
Yes.
It's just strange. Everyone is frozen. No, okay. I will just keep going. So what I'm going to do is look at this factorial, p minus 1 factorial, and I'm going to split it into 2 parts. The first part is going to be the first n squared terms, n squared factorial, and then the leftover terms at the end. There are not many leftover terms, just O of n of those terms. So now I'm going to look at this n squared factorial and look at what that looks like. So here's an example with P being that crazy prime I showed you before, which is about 16 trillion. So n is the square root, which is about 4 million. So I can split up this product into groups of n terms. So the first product will be the first n integers, 1 up to n, and then the next product will be the next n integers. And I keep going like this in blocks of n. So I get n groups of n integers, and then I have this leftover terms at the end. And it turns out to be about 2.5 million. So certainly less than n. And then Strassen observes the following. He says, well, we can write this product in the following way. I write down this polynomial, f of x, which is x plus 1 times x plus 2, and so on, up to x plus n. So this is a polynomial with about 4 million terms. And I evaluate this polynomial. First of all, it's 0, right? That's f of 0. That gives me the first n terms. And then I evaluate at n. That's n plus 1 times n plus 2. So that gives me the next n terms, and so on. I evaluate this at n points. And the product of all those values will be the value that I'm searching for. So what he does, he says, okay, step 1, I'm going to compute these coefficients of f of x. So I actually expand out this product and work modulo with the coefficients taken modulo p squared everywhere. So that is a polynomial of degree roughly square root of p. And then I'm going to evaluate that polynomial quickly at those endpoints. And I'm going to use a fast multi-point evaluation algorithm for this. And this eventually also reduces to fast multiplication. And then I multiply these values together and the leftover terms, and this gives me the product modulo p squared. And each of these steps, the complexity is only essentially square root of p. So we get a square root of p algorithm for computing this Wilson quotient. And this algorithm I've just described is in fact the best known algorithm up to some small logarithmic factor improvements for computing a single Wilson quotient. Now, this is in fact what Edgar Costa and I were doing. We were implementing this when we came across what Robert Goebbels was doing. And it would have taken, to get to 20 trillion, it would have taken us about 1 billion CPU years to do this. So obviously, you know, I mean, maybe there are people in the audience who do, you know, astrophysics or protein folding and get to use some really big computers. And for them, probably 1 billion CPU years is just a drop in the bucket. But for a poor number theorist like me, that's unaffordable. So we have to work a bit harder and be a bit smarter. And Robert came up with this brilliant algorithm, which does this in essentially linear time. So you can compute all the Wilson quotients simultaneously up to some bound n in essentially linear time. And it means that the average time per prime is actually polynomial. It's log p to the 4th, as opposed to square root of p, which is much worse. And we were able to get up to this bound in only about 125 years of CPU time, which is much more manageable. Now, I don't have time to explain this algorithm in detail, but I want to give you the basic flavor of it. So I'm going to explain it in one slide. It uses this gadget called the accumulating remainder tree. And I should stress that this idea, I mean, this could have been invented in the 1970s. It's amazing that it got missed by so many people for so long until this master's student discovered it. So the numbers we want to compute are at the bottom of the tree. So for example, 4 factorial modulo 5 squared, that's the Wilson quotient for p equals 5, and 6 factorial modulo 7 squared. I've also got 8 factorial modulo 9 squared, which is a bit silly because 9 is not a prime, but it doesn't matter. It doesn't hurt to compute that as well. And then basically what you do is you start this quantity at the top of the tree, and if you stare at this for a few moments, you'll see what the pattern is. And at each point, you sort of work down to the 2 children nodes of the tree. So for example, here at this node, I've got 8 factorial modulo 9 squared times 11 squared times 13 squared times 15 squared. So I actually have this number, modulo this number, and then I can go both directions down this tree. So to go to the left, I just have to divide by 9 squared times 11 squared. And I do this as a large integer division. And to go right, I have to divide by 13 squared times 15 squared. And I also have to multiply by the missing factors. The missing factors here are 9 times 10 times 11 times 12 to get me up to 12 factorial. And it turns out that if you do this and you do everything using fast arithmetic, then all of this takes essentially linear time. So very, very clever algorithm. Okay, so that's all I'm going to say about Wilson primes. So I'll now move on to Bernoulli numbers, another favorite topic of mine. So let me remind you first of all what the Bernoulli numbers are. So they're a sequence of rational numbers, and there's various ways you could define them. So I'm going to use this this generating function x over e to the x minus 1. And if you look at the coefficients, you write them as bn over n factorial, where the bn are the Bernoulli numbers. So it's easy to prove that all of the odd index Bernoulli numbers are 0 except for b1. And here are the first few even index Bernoulli numbers. So they look pretty tame for a while, 1/6, 1/30, 1/42. Then you have this crazy 691, and then it goes back to 7/6. They're pretty weird looking numbers. But they have many applications. So perhaps the prototypical application is there are formulas that they show up in formulas for sums of powers. So for example, the sum of the 10th powers of the first k integers will be a formula involving Bernoulli numbers. They also show up in the Euler-Maclaurin formula, which has a lot of applications in pure and applied mathematics. So this lets you approximate sums by integrals and vice versa. They show up in the theory of cyclotomic fields, which hopefully I will discuss in this talk a bit later on if I still have time. And then they turn up in lots of other areas, stuff I know nothing about. So apparently they show up in the theory of homotopic groups of spheres. I know nothing about this topic, but they're very important there as well. And I'm sure plenty of other applications. So one very nice application is a famous formula of Euler. So he famously worked out the sum of the reciprocals of the squares. He showed that this is equal to pi squared over 6. And then he generalized this and gave a formula for the sum of any even power of the reciprocals involving the zeta function. So here's the formula. So for example, you get this formula for the sum of the 12th powers, and you get this 691 showing up. That's coming from the 12th Bernoulli number. So the Bernoulli numbers have a very important place in the history of computation because well, there's some controversy about this, but it is arguable that the first computer program was a program for computing Bernoulli numbers. This was written by Ada Lovelace for a hardware platform that unfortunately never existed in reality, but was only in the mind of Charles Babbage. He ran out of money, or ran out of the British government's money, before he was able to build it. So I guess there could be some debate about what exactly is the first computer program. It's a bit like asking, what is the first novel? I mean, it's a question of definition, but certainly it was a non-trivial program, and I'll say a bit more about it in a moment. So what she did is she used this recurrence formula expressing the nth Bernoulli number in terms of all the previous Bernoulli numbers using this formula shown here. So I want to show you this program. So this is actually what she wrote. And this is, in fact, I should stress this is only a small part of the program. It continues off to the right and it continues down the page quite a long way. But to make it legible, I decided just to show you the top left corner of it. So you can see this looks to me very much like some kind of assembly language, right? You have each step is showing you which registers you're operating on, which variables, and it's telling you what the operation is. So, in step 1, you're multiplying variable 2 by variable 3, and you store the result in variable 4 and so on. And she's also got a sort of commentary column showing you what is being computed at each stage. So, I mean, I think this qualifies as a computer program, and it has a loop later on. So perhaps the first ever loop written down, because it has to actually apply the recurrence. I don't know how the hardware handled the loop, but anyway. Something else about this program that's quite interesting is it has a bug. In fact, I believe it has several bugs. I found a very interesting discussion about this on a blog post, someone who'd analyzed this algorithm carefully, and there's a few people have tried to implement this algorithm in modern computer languages, and they've noticed this bug and other ones. So you can see in step 4, we're supposed to divide v4 by v5, but instead we divide v5 by v4. So perhaps if your definition of a computer program is a sequence of instructions containing a bug, then this qualifies as the first computer program. I think that's pretty fair. So the second computational problem I want to talk about is given a number n, to compute the first n Bernoulli numbers as exact rational numbers. Now, Ada Lovelace's program doesn't exactly solve this problem. She does compute the first n Bernoulli numbers, but only as fixed precision approximations. And this is just because of the architecture of the analytical engine. Its registers were 50-digit floating point numbers or fixed precision numbers. Interesting, by the way, that it's 50 digits. To the modern programmer, that seems like a lot. I mean, I'm used to 16 digits, which is the traditional double precision. I don't know why he went for 50. But anyway, that's what it does. But it doesn't compute them. The program doesn't compute them as rational numbers because the numerator and denominator of these Bernoulli numbers grow with n. So to illustrate this, I want to show you another paper. This is from 1840. This is a paper with basically a list of Bernoulli numbers up to well, the numbering is different. This would be B62 in my notation. And you can see, first of all, that the numerators and denominators, well, the numerators are growing. The denominators are a bit irregular, but he's given the factorizations of the denominators and a little bit about the factorization of some of the numerators. But this paper is quite important because for a long time this was the table of Bernoulli numbers that people used when they needed Bernoulli numbers of large index. And it also is interesting that in 1840 it was possible to publish a paper which is just a list of Bernoulli numbers. I don't think we can get away with that these days, unfortunately. That would make life much easier if we could do that. Okay, so in terms of the growth, I'll just briefly state what the facts are. The numerator of the Bernoulli number of Bn grows, it has essentially n log n bits, and the denominator has at most some multiple of n bits. We can probably prove something better than that, but I don't know what is the best result. I suspect n is not, O of n is not sharp. But this is not hard to prove, and I've got a sketch of a proof here, but I won't go into that. So using this information about the growth of these numerators and denominators, you can figure out how much space you need just to write down the first n Bernoulli numbers, and it's roughly quadratic in n. So if you tried to use the method that Lovelace used, the recurrence method, the amount of work you'd have to do to compute the first n Bernoulli numbers would be roughly cubic in n. And the reason is that every time you compute the next Bernoulli number, you have to at least read through all the bits of the previous ones. So that's n squared work for each Bernoulli number, and then n cubed to compute all of them up to n. So a few years ago, Richard Brent and I proved that in fact you can compute the first n Bernoulli numbers in essentially quadratic time. We only give up a log n factor compared to the amount of the number of bits we need to write down. So I want to explain this algorithm briefly to you. So first, I'm going to normalize the denominators. I'm going to multiply by essentially 2 to the n minus 1 to get rid of the denominator. And the resulting numbers are called the Gnocchi numbers. So this is a sequence of integer coefficients. And you can work out the generating function. Instead of e to the x minus 1, we basically have an e to the x plus 1 in the denominator, but otherwise very similar. So that's some sequence of integers. And I'm just going to show an example of how you might compute the first 10 Gnocchi numbers using this method. So what you do is you consider this series, e to the x plus 1, and I'm going to clear denominators by multiplying by 9 factorial and write down the first few terms. So that's very easy to do. And I've stopped at x to the 9. After that point, you would still have some denominators coming from the larger factorials. And then I'm just going to evaluate this power series at a suitably small power of 10 in this case, because I'm working in base 10. So in this case, 10 to the minus 4. And I just discard the higher order terms. They're not going to contribute. And so evaluating at 10 to the minus 4 pretty much amounts to just writing down these underlined coefficients in the right place. So 1, and then 9, and then 72, and then 504, and so on. Here they start to overlap a bit, so you might need to do some carry propagation, but that's pretty easy. So you can do that in essentially linear time. Then you use a fast division algorithm, so floating point division algorithm, to essentially compute the reciprocal of this number, scaled by some appropriate factorial constant, and you get this number here, and you'll notice there's lots of zeros and nines in there. So I'll just copy that onto the next slide. So that's the same number as before. And then these underlying numbers, you can sort of read off the integer coefficients of the corresponding power series. And that's because my 10 to the minus 4 has sort of given me enough space between the coefficients. They don't overlap. So I can decode these coefficients. and then I can just get rid of all the scaling factors and recover the original power series that I wanted to compute. So the basic idea is you're inverting the power series by evaluating at an integer, at a sort of integral point, and then inverting the corresponding real number. It's like some sort of homomorphism properties being used there. And then you do a bit of numerical analysis to check that you've got enough, you can actually recover the coefficients. And this gives you the Gnocchi numbers. So it all comes down to that fast division step, which in the end depends on fast Fourier transforms. That's what's making this algorithm work. Okay, now I think it's important to have a short break in the middle of a difficult mathematics talk. So I've got here a trivia quiz. So as you know, there was a large family of Bernoullis who did lots of interesting things in mathematics and physics and other fields. And I've picked 3 of the most famous Bernoullis here: Bernoulli A, Bernoulli B, and Bernoulli C. And the question is, which one of these has the Bernoulli numbers named after them? And I will give you a few moments to cheat by looking it up on Wikipedia. So the answer is Bernoulli C. This is Jacob Bernoulli. So he's responsible for Bernoulli numbers and also a lot of other things, including the law of large numbers in statistics. His brother is Bernoulli A, Johann Bernoulli, and he did a lot of early stuff in calculus, among other things, L'Hopital's rule, which doesn't seem very fair, that we call it L'Hopital's rule. It should be Bernoulli's rule, but maybe too many other things are named after Bernoulli. And then I also mentioned Daniel Bernoulli, who's responsible. So this is Johann's son, so I guess Jacob's nephew. And he's responsible for Bernoulli's principle in fluid dynamics, which is what keeps aeroplanes in the air. There are not so many airplanes in the air at the moment, unfortunately, or fortunately. Okay, so back to some mathematics. So the third computational problem I want to talk about is, what about computing a single Bernoulli number, B sub n, just by itself, without computing all the previous ones, as an exact rational number? So this might seem like a very artificial problem, and I agree it is. You know, who cares about computing the 100 millionth Bernoulli number? That doesn't really have any possible application that I can think of. But what I'm interested in about this problem is there's a complexity question, which is interesting. It's saying something about how complicated these numbers are. Right? It's some very strange measure of the complexity of this sequence of numbers. So here's some other analogous examples. If you look at the Fibonacci numbers, that's a much simpler sequence of numbers. There are good algorithms for computing the nth Fibonacci numbers. It has a linear number of bits, and you can compute it in essentially linear time. Right? That's not hard to do. The nth factorial is another example. That has n log n bits, so essentially linear in n, and you can compute it in essentially linear time using what's called a product tree, and there are even faster methods. So for Bernoulli numbers, there are n log n bits to compute if we want to compute that. Can we compute this number in essentially linear time? You know, like n times the power of log n, for example. So interesting question. So here's a first attempt at a fast algorithm for computing a single Bernoulli number. This is called the zeta function algorithm, and it's been discovered maybe a dozen times independently. And I document this in our paper, in our 2010 math comp paper. Sorry, on my 2010 math comp paper. Thinking of a different paper. So basically, what you do is you use Euler's formula backwards, right? Instead of using the Bernoulli number to compute the zeta function, you go the other way. You approximate the zeta function, zeta of n, by using this Euler product. You compute enough terms of this Euler product to compute zeta of n accurately as a real number, and you use that to read off the Bernoulli number, because you know what pi is and you know how to compute factorials. So you can work out the details of this, and I won't go into the details, but you can do this in essentially quadratic time using fast multiplication. It's basically because you need roughly n terms in that product, and each of them has roughly n bits. So you get something like quadratic time. Now the problem is that this running time bound is essentially the same as the algorithm that Richard, Brent, and I discovered for computing all the Bernoulli numbers up to n. So you haven't saved anything. In fact, I'm not even sure that you save a log factor. You may save a log factor. Yeah, that's a long story, but in any case, it's very close. Here is a second attempt. So this is the 2010 paper I was referring to. This is a different algorithm from the zeta function algorithm. what you do is you use congruences for the Bernoulli numbers modulo small primes. So here's an example of such a congruence. You take the sum of the nth powers modulo p from 0 up to p minus 1. So you actually have to do that modulo p squared and then divide by p to get the result modulo p. And you can do this for a bunch of small primes. This is for a fixed n. You do this for many small primes p, and then you reconstruct the result, the actual Bernoulli number, using the Chinese remainder theorem. There are fast ways to execute the Chinese remainder theorem explicitly. And it turns out this is faster in practice, at least for numbers up around 100 million, than the zeta function algorithm from the previous slide. But when you analyze it in theory, you again get a quadratic time, essentially quadratic time algorithm. And so this is very interesting. We've got two completely different algorithms for computing these Bernoulli numbers, which are quadratic time. So you might say, well, okay, like what Kolmogorov said for multiplication, maybe n squared is the best you can do. Well, in fact, it is not. There is an algorithm that does this in n to the 4/3 time. So why 4/3? That is a great question. I don't really know. That's just what comes out of it. And again, this relies on fast multiplication. So I'm going to explain briefly how this works. So the starting point is to look at higher order congruences. So I showed you on the previous slide a congruence for the Bernoulli number modulo p. So there is also a congruence modulo p squared. So here it is. So this is the same term we had before, k to the n, but now there's this new, slightly more complicated term. And in fact, you can generalize this to any fixed power of p that you like. So here is the formula for Bernoulli number modulo p to the s plus 1. So it involves these binomial coefficients, and it involves the Bernoulli numbers up to s, which is very nice. So number theorists in the audience might realize this is connected somehow to the p-adic L functions associated to the trivial character. So there's some interesting stuff going on there. Now, this formula gives you more information than the original congruence modulo p. So you might think, well, I can use that to compute the Bernoulli number more efficiently. The problem is it's also more expensive to evaluate this formula because it has more terms. And so what you might try doing is you might say, well, if I choose the precision, the power of p differently for each prime, and I try to combine the information from different primes, maybe I can optimize things and do better. Well, you can't. It doesn't work. You still get n squared. Very frustrating situation. So how do we do better? Well, what we do is if you look at that sum in the previous slide and you play around with it, you discover that it can be written as a polynomial in p over k. And what this means is that you can evaluate this for lots of values of p, lots of primes, and lots of values of k simultaneously using fast arithmetic again, using fast multi-point evaluation algorithms. So this is what I did in my 2014 paper, and then you analyze how many primes you should use and what precision you should use, and it turns out that when you do that, you get an n to the 4/3 algorithm. So one question I'm very interested in is, can you do better than that? Can you get down to quasi-linear time? There's no obvious obstruction to it, and this is a problem I come back to every now and then, have a think about, but I've made no progress with it since that paper. This algorithm, by the way, has not been implemented. So Edgar Costa and I made an attempt some years ago, and we just got distracted by other things, so that's still something that needs to be done and looked at. We don't know if it's efficient in practice. Okay, the last thing I want to talk about briefly, I think I still have a few minutes, is irregular primes. So first of all, I'll explain to you what irregular primes are. So the story goes back to the beginning of algebraic number theory and the work of Ernst Kummer. So he managed to do some of the first really non-trivial work on Fermat's last theorem. So he was able to prove Fermat's last theorem for a whole bunch of exponents. So the theorem he proved is that if p is a prime which does not divide the numerators of a bunch of Bernoulli numbers, b2 up to p minus 3, then Fermat's last theorem holds for that exponent p. So in other words, there are no non-trivial solutions to the equation x to the p plus y to the p equals z to the p. So non-trivial integer solutions. The trivial solutions are like 1 plus 0 equals 1, for example. So apart from those easy ones. And a prime that satisfies this Kummer's condition is now called regular. and one that does not is called irregular. And I suppose Kummer originally hoped that all primes would turn out to be regular, but they don't, of course, and I'll show you that in a moment. But in the modern language of algebraic number theory, this condition is equivalent to saying that P does not divide the class number of the pth cyclotomic field. So he did a lot of computations by hand to test irregularity, and he knew something interesting was going on with 37. And I think he also found that he also discovered that I think for 23 is the first time you have a non-trivial class group, and then 37 is the first time that the order of the class group is actually divisible by P, making it an irregular prime. And he did a lot of computations, and there's this sequence of papers where he computes further and further and gets up to 157. So he found all these irregular primes. So here's an example. 37 is irregular according to his criterion because the 32nd Bernoulli number has a numerator divisible. It happens to be divisible by 37. And so we say that 37 and 32 is an irregular pair. So it can happen that one prime can belong to more than one Bernoulli number. So for example, 157, it divides the numerator of two Bernoulli numbers, the 62nd one and the 110th one. So that can happen as well. And I'm pretty sure Kummer knew this as well. So the next computational problem I want to talk about is to compute all irregular pairs for primes up to a given bound. And originally, Fermat's last theorem was the motivation for this problem. But these days, Fermat's last theorem got proved by other means. But it's still interesting for people working in cyclotomic fields. So here we have, for example, the Kummer-Van der Waals conjecture is still an unsolved problem about cyclotomic fields. It claims that the class number of the pth of the maximal real subfield of the pth cyclotomic field is not divisible by P. This is a very hard problem. There've been a few incorrect proofs over the years. Some people think it's true. Some people think it's false. I don't know what the answer is supposed to be. So a little bit about the history of early computations of this problem. So Stafford and Van der Waals did a bunch of papers. They went up to 613, not quite by hand. They were using a sort of desktop calculator. I'll show you a picture of one in a moment. But they were mainly using congruences modulo P rather than using the old tables of Bernoulli numbers. And they were using tables of indices, which are basically discrete logarithms to help them do their arithmetic. So here is a picture of the kind of machine they were working with. I don't know exactly what they were using, but this is the kind of machine that was used in that era. So I guess you turn the handle to do your computation. And he is also very interested in computational complexity. So here's what he writes. As to the time required for the work on a particular prime L, close to the value 600, so that's about as far as they went, in a test for regularity, a person experienced in this work requires about 40 hours to complete the test. So this is a good week of work for one of these primes, provided the prime is of the form 4n plus 3. If it's of the form 4n plus 1, you can save about a third of the time. And it's fascinating that with modern algorithms, we see the same kind of things happening. Certain congruence classes of primes admit various speedups, which is very important in practice. So here is a table of computations of irregular primes. This is a problem that's been revisited many times over the years. So I got involved in this problem in 2011. I ran a computation with Joe Buehler, mainly on a supercomputer at the University of Texas. And then more recently with, this is actually a trio of Australian mathematicians, Bill Hart and Wilson Ong. So we went up to 2 to the 31 and we checked all the conjectures and so on. Now, I'm just about out of time, so I think I might skip over this stuff. Basically, originally there were quasi-quadratic time algorithms, and at some point they switched to quasi-linear time algorithms. And this very briefly explains how that algorithm works. So I think I will skip over that. It just involves a power series inversion. And I'll just briefly summarize the computation that I did with Wilson and Bill. So we did this computation for about 100 million primes up to 2 billion, and the total CPU time was about 1,000 years of 1,000 core years of CPU time. This is the largest computation that I've been involved with, and I think it's still a pretty big computation in number theory domain. There are certainly some bigger ones, but it's still reasonably big. this ran for about a year on 9 compute clusters in the US and Australia. So I was fortunate to get access to all those machines. And the program spends almost all of its time multiplying polynomials of high degree. So it really spends all its time doing fast Fourier transforms. So we verified the standard conjectures over this range, and we found, so this is just showing off that we found the first prime which has 9 associated irregular indices. So finally, I'll just mention that, of course, in this talk, I've only given a very, very brief sample of the kind of problems that you can attack using fast arithmetic in number theory. And here is a brief list of a few other problems. And I think I will finish up there. Thank you very much.